Chapter 15, revision questions. First of all the formulas you need to know for the low pass bandwidth, filter bandwidth of a bandpass filter, the center frequency of a bandpass filter, quality factor of bandpass filter, the damping factor, closed loop voltage gain, critical frequency for second order Sally-K filter, center frequency of multiple feedback filter, and the gain of a multiple feedback filter. Let's start. The green line represents the response for a Butterworth, Chebyshev filter, or the Bessel filter. In this case, that is a Chebyshev filter. You can see there, they've got a little loop like that one there. The blue line represents the response for a Butterworth, Chebyshev filter, or a Bessel. In this particular case, that is the Bessel filter. A filter that is superior for its pulse response is a Butterworth, Chebyshev, or a Bessel filter. That is the Bessel filter. From a table for a 4-pole Butterworth filter, the gain required for the second stage is equal to 2.235. That is for the 4-pole. For 2-pole Butterworth filter, assume that R1 is 39K. From the choice given, the best value for R2 is equal to 68 kilo ohm. The type of active filter shown is a 2-pole low pass, or 2-pole high pass, a 4-pole low pass, a 4-pole high pass. This is a 2-pole low pass because it's got a capacitor in the feedback loop. The approximately roll-off for a filter shown, minus 20 decibel, minus 40 decibel per decade, minus 60 decibel per decade, minus 80 decibel per decade. In this case, it is a minus 80 decibels per decade. A good choice for a high Q active band pass filter is cascade high pass and low pass filter, a multiple feedback band pass filter, a state variable band pass filter, an inverting amplifier with a resonant filter. The correct answer is a state variable band pass filter. A filter shown forms a band stop filter, band pass filter, low pass filter, a high pass filter. That is a band stop filter. For the sweep frequency measurement, the signal on the X channel of oscilloscope is a sine wave that changes frequency, a sawtooth wave, a square wave, or a DC level. This is a sawtooth wave. There you can find all the answers. Let's go with the following questions. That's true or false questions. The bandwidth of a bandpass filter is the difference between the two cutoff frequencies, and that one is true. Butterworth filters have a roll-off of 40 decibel per decade and widely varying output in the pass band. It's false. A high-pass filter passes high frequencies easily, attenuates all other frequencies. That is true. A low-pass filter attenuates low frequencies. That is false. A band-pass filter passes all frequencies within a specific band and blocks for other frequencies. That is true. Refer to the figure below. This is the frequency response curve for a low-pass filter, a high-pass filter, a band-pass filter, or a band-stop filter. To look to that one, that is a band-pass filter. Refer to the figures below again. This frequency response curve for a low-pass filter, high-pass filter, band-pass filter, band-stop filter. That is a band-stop filter. Refer to the figure below. The circuit was checked for proper operation and FQ was corrected, but the voltage gain is 1. The cause of this problem might be the 1.2 kilo ohm resistor is open, the capacitor is shorted, RA is open, and RG is open. The correct answer is RG is open. Refer to the figure below. This circuit is known as and the roll-off rate is, this is a low-pass filter, 60 decibels decade, high-pass filter, 20 decibels per decade, a high-pass filter, 80 decibels per decade, bandpass filter 80 decibels per decade. The correct answer is high-pass filter with 80 decibels per decade. Refer to the figure below. The cutoff frequency for the first filter section is, and the cutoff frequency for the second section is equal to, higher than, lower than, none of the above. No, that is equal to. So refer, the cutoff frequency for the first filter section is equal to the cutoff frequency of the second section. A high-pass active filter has a cutoff frequency of 1.23 kHz. The bandwidth of a filter is 2.46 kHz, 1.23 kHz, 6.44 kHz. Cannot determine. In this particular case, that we cannot determine. A low-pass filter with a roll-off rate of 60 decibels per decade is needed. The best combination to use is a two-pole filter followed by another two-pole, two single-pole filters in series, a two-pole filter followed by a one-pole, none of the above. The correct answer is C, a two-pole filter followed by a one-pole. A high-pass filter has a resistance of 47 kilo-ohm, capacitor set of 0.002 microfarad. So the cutoff frequency 1.69 kHz, 10.6 kHz, 3.39 kHz, none of the above. The correct answer is 1.69 kHz A. A pole is a network that contains a resistor and a capacitor, a resistor and an inductor, a capacitor and an inductor, two resistors and one inductor. The correct answer is a resistor and a capacitor. Maximally flat frequency response is common name for Chebyshev, a Bessel, a Butterworth filter, or a Colpitts, a Butterworth filter. A single RC circuit produces a roll-off rate of minus 20 decibel per decade, minus 6 decibel per decade, minus 40 decibel per decade, or A and B. In other words, 20 or 6. In this particular case, that's minus 20 decibel per decade, as well as minus 6 decibel per decade. A low-pass filter has a cutoff frequency of 1.23 kHz. Determine the bandwidth of a filter. Is it 2.46, 1.23, 644 Hz? Not enough information is given. It is 1.23 kHz. Above the cutoff frequency FC, a low-pass filter, the output voltage does not change, doubles for every 1 kHz increase in frequency, increases or decreases. Correct answer is decreases. The center frequency of a bandpass filter is always equal to the bandwidth, geometric average of the cutoff frequencies, bandwidth divided by Q, 3 decibel frequency. That is geometric average of a cutoff frequency. And bandpass filters are designed to pass a band of frequencies between FC1 and FC2, or a band start and band stop, 1 kHz and 10 kHz, 1 kHz and 10 megahertz. The correct answer, FC1 and FC2. Low Q filters are circuits and high Q filters are circuits. What kind of circuits? A low Q filter, is it a band pass or band stop? Or is it wide band pass or narrow band pass? Low band pass, high band pass, low order, high order filter? The correct answer is low Q filters are wide band circuits, and high Q filters are circuits with a narrow band pass. A notch filter is all pass filter, band pass filter, band stop circuit, or time delay circuit. A notch filter gives you a band stop circuit. A type of filter response with a ripple pass band is the Butterworth, Chebyshev, inverse Chebyshev, or the Bessel. Correct answer is for Chebyshev. The filter response characteristics that distorts pulses for least is the Butterworth, Chebyshev, elliptic, or the Bessel. Correct answer is for Chebyshev. The filter with slowest rollout rate is Butterworth, Chebyshev, elliptic, or Bessel. It is for Butterworth. The damping factor, DF, of an active filter determined by the positive feedback of a circuit, negative feedback of a circuit, the number of poles, the Q of a circuit. Correct answer is the negative feedback of a circuit. Sallen key filters are also called ICFS filters. multiple feedback filters, biquadratic filters, state variable filters. The correct answer is the VS filters. By cascading low-pass filters, what can be improved? The bandwidth, the roll-off rate, or the Q rating, or the phase shift, the roll-off rate. A multiple feedback bandpass filter uses a minimum of 2 op-amps. Minimum uses a narrow band or high Q filter. Is used for wide band low Q filter. Is also known as a Sally-Key filter. It uses for the wide band low Q filter, in other words, number C. The state variable filter is difficult to tune, uses fewer than 3 op-amps, has high component sensitivity, has a low pass or high pass band pass output. The correct answer, it has a low pass, high pass, and a band pass output. The Q state of variable filter is controlled by the ratio of R5 over R6, the product of R5 times R6, the ratio of a feedback resistor, both A and C, above. So the correct answer is both A and C above.